Chapter 5 of the book introduces us to light. Okay, the nature of light, some of the physics behind light, and how light works. Now, why do we care about how light works? Well, because that's all that we see from stars, literally. That's all that we get from stars is the light, from the stars. And so understanding how light works helps us understand how stars work, because you make light different ways. And so if we can measure the kind of light that we're getting from a star, that will tell us about the star. It'll tell us all kinds of things about the star. And so that's why we want to understand how light works. Now, chapter 17 of the book uses some of these concepts of light, but it uses the ideas from chapter 5. And so I'm not assuming that you've had the other half of the class before this. So we're going to go back to chapter 5, talk about light, then go back to chapter 17. So there's different ways of making light. One way of making light, pretty straightforward, and the first thing we'll be talking about in our next lecture is what we call thermal radiation. Thermal radiation is basically, as the name sounds like, it has to do with heat. Basically, atoms and molecules have electric charges in them, and when they move back and forth, when it gets hot, they move back and forth. When they move back and forth, you start changing electric and magnetic fields. Well, we know that light is electric and magnetic fields. So if light is electric and magnetic fields, changing electric and magnetic fields, moving the molecules back and forth makes light. So anything that is not at absolute zero is so cold that molecules don't move, that's going to make light. And so it's going to radiate energy off into space. Now, we talked about previously the electromagnetic spectrum, different wavelengths of light. They don't all have the same amount of energy. For example, if it's not very active, it's going to be giving off very low energy radiation, microwaves. If it's more active, it's going to give off infrared light. That has more energy than microwaves. If it's even more energetic, it's going to be giving off visual light. So that means it'll start getting like red hot. Okay, so it'll be giving off visual light that you can see. It gets even more active. This would be like if you're doing arc welding or something like that. It gets so hot, it gives off ultraviolet light. You can actually sunburn your eyes, with welding. Because of the ultraviolet light given off because it is so hot. In fact, the outer part of the sun, the corona of the sun, is so hot, it's giving off even more energy than ultraviolet light, and if you remember, that's going to be X-rays. So X-rays are even more energetic. And so the different temperatures, so you can work backwards. With thermal radiation, you can work backwards. We call it black body radiation because the math of how something is absorbing energy is the same as it giving off. So a black object absorbs the energy perfectly, and so it also gives it off perfectly. And so black body radiation or thermal radiation, if you measure it precisely, it will tell you several things: the temperature and the size of the object giving off the radiation. Okay. Another way of getting light is atomic radiation. The atom itself, the electrons. You've got the nucleus, you've got the electrons out here. The electrons, they can go from one energy to another energy. When they go from one energy level to another energy level, physics says you have to conserve energy, so the energy has to go somewhere. It goes away in the form of light. Okay, so that would be an emission spectrum. And so we'll talk about how that works. Different elements have a unique set of emission spectra, different colors of light they give off, and only those colors of light. And so what you discover is that when you look at this, then that's going to be like a fingerprint. You can then look at the spectrum of something and find out what elements made it up, what kind of atoms made it up. Fluorescent lights, that's another way of making light that involves the atoms themselves doing it. Or LEDs, that's another example here in which you're talking about atomic levels, atomic energy levels. It's a little bit more complicated than that because it's a semiconducting device. But basically you have different band gaps, and so when the electrons go from one energy to the other, it gives off the energy somehow in order to conserve energy, and that can be given off in the form of light. And so those are different ways of making light. Each of them is different, and each of them makes a different kind of light. Incandescent bulbs. Old-fashioned incandescent bulbs make light because they get hot and they give off light. Compact fluorescent bulbs make light in a different fashion. It's a combination actually of emission spectra and fluorescence. And then LEDs make light in an even different way. If you actually look at the light given off by all the different bulbs, it's actually slightly different. So that means things look different in the camera under different kind of lighting, because each kind of light has different proportions of all the different colors of light in there. And so that actually has an impact too. Human body interacts with light, and so different colors of light have a health effect on you. So that's one of the things that they're starting to realize, is that the wrong kind of lighting in your home can actually be unhealthy. And so that's something that is starting to come out. Wrong kind of lighting in the city can be unhealthy. We already know that light pollution, stray lights at night, have an impact on migratory animals. Part of the decrease in certain kinds of migratory animals, birds dying off, has been traced back to light pollution at night. And so that's another thing. And light pollution also has been traced back to health issues. Too much light pollution, and your body's designed to have day-night. So if you take away the night, then your body responds differently, and they've linked, for example, cancers and things of that sort to people who never experience darkness. And so that's again, light interacts with you. And this has to do with how we detect light. Light has energy. So when light hits things, it can cause chemical reactions. You're all familiar with things fading in sunlight, or the sunlight breaking down certain kinds of plastics, ultraviolet light. That's a chemical reaction occurring due to the light. Your eyes, this is how you actually see light. This is how you see, is light goes into your eyes, and there's different chemicals in there in the different detectors in your eye. You have rods and cones. You have 3 different types of cones and 1 type of rod. And so that there's different chemicals in there that respond to the different kinds of light, and that's how you see color, at least in the cones. Okay. There's also electrical response. Light is electric and magnetic fields, so light can actually trigger an electrical response. That's how your digital camera works. It picks up light electrically. So the light hits a semiconducting chip, knocks electrons loose, and now we have a way of measuring that. That's a digital camera. Finally, there's another way of detecting light, and that's nuclear. We're not going to really talk about that. That's beyond the level of this class, but certain extremely energetic forms of light. For example, X-rays, or especially gamma rays, can excite the nucleus of an atom. And so that's another way of potentially detecting light, or detecting the effect of light. But we're not going to normally worry about that. You know, as far as we're concerned, chemical reactions that happen to your eye, happens when things fade in the light. That's how the old-fashioned film cameras worked. That was a chemical reaction. Or electrical interactions. That's going to be how radio waves work, because radio waves are in fact lights, or radios, radio telescopes, and CCDs, which are the core of digital cameras. That's all electrical.